All right. Thanks very much, Ashley, and thanks for sticking around until the end of the track for the Make Browsers Cry talk. My name's Clay. I'm a developer advocate here at New Relic, and just a little bit of explanation on what I mean when Make Browsers Cry. Browsers obviously don't have physical eyes or tear ducts, but the idea here is that we make a series of technical decisions, and those decisions ultimately have some impact on page load time, how quickly some application or site loads in the browser. And this talk is really getting into some of the details of those decisions and how those can ultimately impact how people experience the sites and applications we build that run in the browser. Typical, you've seen this slide before. It's the end of the day of the track, and a shout out to the legal team for keeping us all compliant with this stuff. But me, I'm not an attorney, in case it's not obvious, but just a little bit about me. I have been making pages and apps for a while, and I think, being perfectly honest, if I were to survey everything I've ever built that's run in a browser, most of those things I've built would not ever win trophies or awards for super great performance or following all of the best practices. For example, I'm kind of ashamed to say that I have built a website that was blocked by more than 9 AJAX requests, completely blocked rendering, massive spinners everywhere. I've also incorrectly implemented browser caching, e-tags in particular, different headers. It seemed to be faster, but there were some edge cases. I've also overused web fonts. I think fonts can really add some nice design to a site when you're not doing much of anything else, but I have overused them and paid the performance penalty. And earlier on, in the early 2000s, I definitely unironically used the blink tag. So between all those things, I think in terms of talking about the technical choices that we make that can impact performance in a negative way, I'm absolutely willing to share some of those things. And just good news disclaimer that none of those things I've done while I've been employed by New Relic. So if you're a New Relic customer, rest assured that I'm not doing any of these things in our production systems. I don't know. I think for every kind of talk that gets into web performance or kind of the top 10 tips and tricks you can use to make a fast website, the truth is, and what everyone will eventually admit, is there's really no silver bullet. There's nothing you can really do, no magic technology or framework that will suddenly make everything faster all the time. And I think it's good just to be very realistic about that and to admit that it's a fairly complicated space. There are many, many things you can do, and you can do many things at different layers of the stack. It's really not just about the browser. It goes all the way down to the infrastructure. And we're actually going to be exploring those different layers of the stack in the course of this talk. And I think why I really wanted to talk about things that make browsers cry, technical choices that impact performance negatively, is I think there's actually something very valuable in learning or seeing things that aren't necessarily very good in terms of end user experience, so you can avoid them, but also just to understand the process of identifying those problems in the first place. I think if we think about the general model, and I've been thinking about this for a bit now, of how we consider a modern browser application. If you were maybe in an interview or just kind of a high-level whiteboard session, you would probably immediately jump to the client-server model, which predates the web. It's been around for a while. The idea, as I'm sure you're aware, is yes, we've got a browser, the client, it makes requests over the network to some remote server. The server sends responses, and through those responses, it constructs some sort of web page or web application. The really interesting thing about this model is it's old, it works, it's a useful abstraction, but in 2016, with modern web applications, we know that there's quite a lot more actually going on when we're building these. Just to name a few, and this is not at all comprehensive, but we are making requests to many servers all over the world. The browser itself is not necessarily even on a desktop. It could be on a mobile device, different types of mobile devices. I'm sure a lot of people have seen that famous chart of Android device fragmentation where it kind of lists the thousands and thousands of combinations and different processing speeds and capabilities of different devices. Through that, you've got different layers of caching. You might or might not be using a CDN. You might be using a CDN for different sorts of static or even dynamic requests. And then when you make a request to say some service or API endpoint that you actually control, increasingly that's backed up by potentially dozens of services. I don't want to use the word microservice, but potentially different services, some combination. And then you also have third-party components as well that you're using to construct your site, maybe analytics, maybe ads. But it's all kind of cobbled together in what we call kind of a modern cutting-edge application. And that's pretty important. And to actually back that up with real data, we actually have a really great nonprofit resource called the HTTP Archive. They essentially crawl the Alexa top 1 million sites. They aggregate it at httparchive.org. And you can actually see some really nice high-level metrics around web performance. You see this in a lot of talks like this. But just to kind of roll through a few of the ones that I think are pretty interesting, is that as of last month, a recent run of the HTTP archive, a single page in the Alexa top 1 million on average makes a request to 20 domains. So that absolutely supports the idea that we're communicating to more and more remote endpoints over networks. Some we control, some we don't. Not surprisingly, if you've used a web page or if you've upgraded your mobile data plan lately, year over year, these are snapshots in September going back 3 years, the average total transfer size, so that's all of the HTML, AJAX, web fonts, CSS, maybe Flash, that's actually being sent in a page, that's not surprisingly increasing, and as of this fall, just around 2.5 megabytes. So we've got more domains, more remote hosts, we've got increasing transfer size, and we've also got a very large number of requests that is also trending up, 107 per page. And that ultimately means for a given page, before it's completely loaded, the run of the HTTP archive run, there's over 100 remote network requests it needs to make to essentially construct that page, maybe send some data to different servers, ads, everything, so comprehensively. So we see this kind of upward trend, which I think also supports this idea that things are not getting any simpler as we build more pages. That's all like really abstract. I think it's sometimes easier to kind of take a real life example. So the Alexa top 10, one of the 10 most trafficked sites on the internet according to Alexa. The worst offender, which I won't mention, it makes 312 requests. You can actually see the the waterfall there. But 312 requests, and here we go. 312 requests, and as it's scrolling down the waterfall that we've captured in Relic Synthetics, 15.4 seconds to render. And this synthetics run was in a geographic location pretty close to where it was being served. So like even though we kind of know that yes, we want to make sure the site's not a massive site, we want to reduce the number of requests, we want to make sure it loads fast for people on desktop connections or mobile connections. The reality, even if your site has hundreds of millions of users, is just more complicated. And I think that's, and just looking at this waterfall, we know, it's probably very difficult to make changes to the site in the first place. So with that in mind, we can kind of iterate on this model and say, well, if you're in a front-end role, which I've certainly been in, the model or a common model is, you're very focused on the layer between the user and the front-end code. So the code and the user interface that actually runs in the browser. Is it fast? Is it responsive? Is it usable? But I think as we've kind of gone on and as the tooling has become more complicated and as the demands of the sites we're building that run in the browser have also become more complicated, the focus on the network, the backend systems, and the infrastructure that powers those systems has become equally as important. And it's something of a new area, and it crosses some team boundaries and silos. But ultimately, I think when we talk about what's needed to make a really fast web page for a global audience, this part, the backend system black mystery box, the infrastructure, and understanding the network is very important as well. And so I think now with that kind of established, that's the general framework, we can ask this question across all those layers, across the browser, how can we, or what technical choices can we make and measure those choices to make a hypothetical page as slow as possible. And we'll bring it back. And so we've got the browser. We've got essentially 4 tiers. And we're going to go through each of these and make some choices and essentially see what happens. But in general, the very scientific methodology will be we'll make choices to confuse the browser. We'll ignore the network. We won't optimize the app or make application unoptimizations, I guess, if that's even a word. And then with infrastructure in particular, we're going to make deliberately not wise choices. So between all that, we want to measure too. So I'm introducing a way to measure it that's just kind of made up for this talk. I'm calling it the meter of broken customer experience. It's pretty straightforward how it works. We want low numbers in this meter. So as it gets higher, the theory goes that the customer would be more frustrated. And I know that's like really inexact and hand-wavy. So we'll actually back it up with some numbers here. So if we look at this from some kind of user experience research, this has been around for a while. I think the studies even go back to the 1960s. But ultimately, some scientists did some things that looked at how people interact with devices and how that actually works. And they came up with this power of 10 scale that you see in different places. But ultimately, one way to look at it is that if some interaction with some device, doesn't even necessarily have to be a computer, takes under 100 milliseconds, it feels like magic. It feels like it's just instantaneous. So that's a really nice bar. To kind of quantify that 100 millisecond bar, they measured the start time for the 100 meter dash at the 2016 Rio Olympics. The gold medalist Usain Bolt had a 155 millisecond reaction time. So this is very fast and getting up, like very much hitting the limits of how quickly we as like humans can actually perceive things happening. An order of 10 higher than that is 1 second, 100 or 1,000 milliseconds. And at this point, the theory is that your mind starts to wander from the task you're trying to achieve. So, for example, you're trying to click a button or something. It takes more than a second. Your mind is likely to wander, perhaps where you're going to eat lunch. In order of 10 greater than that, 10 seconds, you've likely lost the person. You've kind of lost all focus on what exactly it was you're supposed to establish. So I think between this kind of fundamental user-computer device interaction research and a mountain of data from essentially every web company in the past 10 years, Amazon, Google, we know that faster times are better and engage people in a more meaningful way. So to go through this, the real question is, let's make some technical choices that actually increase bad customer experience. And we're going to do this in kind of a simulated lab environment. There's a vanity domain, webperf.rocks. It generates ugly images, some set amount of HTML and CSS. It loads that, and so each request to this domain will be identical. So as we make changes to the underlying code or infrastructure that generates it, we can actually see the delta between our changes. Some background information on this kind of environment. It's running on a public cloud, in this case, Amazon Web Services, using their EC2 service. The architecture is deliberately simple. It's a single binary process written in Go, also monitored in Go using New Relic. The instance size is a fairly large one, a couple processors, I think 8 gigabytes of memory. And the page itself is also deliberately simple. There aren't any iframes, there's no flash, at least initially no serious third-party code. But if we kind of load that page and we just kind of take a snapshot of, well, what's the median load time across different global locations? In this configuration for this page, the starting point is around 1,400 milliseconds. So not great. You'll definitely notice it's loading, but not really terrible. I mean, not that awful either. And it actually has enough meaningful information and enough stuff going on where it can actually see stuff change. We're going to start kind of low on the stack with infrastructure and move our way up all the way to the browser. But the first idea is, well, this is running on some infrastructure. What can we actually do to this infrastructure to significantly slow this page? And I think the thing I did first was, well, what's the absolute cheapest EC2 instance we can run this on? Not necessarily to save like the 30 cents when this simulation was running, but just to kind of really constrict the amount of memory and CPU it could use. And the cheapest thing you can buy on AWS nowadays is a T2 Nano instance. Those are the specs right there. But the idea was, let's switch it from this more powerful instance to this T2 instance and essentially see what happens. And there's a little bit of information about the T2 Nano instance, and there's this interesting disclaimer that I ignored at first that says something kind of promising sounding. It's like, well, it's this high-frequency CPU if your workload utilizes less than 5% of the core on average over 24 hours. Oh, okay. But if I launch this instance, I run this application for about half an hour, it's essentially the same as running on a larger instance, only about 45 milliseconds slower. So actually a pretty good deal because we're drastically reducing the power of the EC2 instance it's running on, and the penalty is quite small. But I actually did go to lunch after this. This is a true story. I did have Mexican food. And I came back, I pulled up New Relic infrastructure, and the load had completely spiked. I thought at first, like, oh no, I wrote terrible Go code, I must have a terrible memory leak, or like maybe I'm generating more traffic than I thought, or that got scaled up unexpectedly. But we're looking at the load numbers, not surprisingly, looking at APM and the web transaction time, the amount of time actually spent processing all the transactions also spiked quite considerably. And not surprisingly, you can see the aptX score also tanking and the throughput also tanking. And the reason behind that, kind of interesting. Well, and one more thing, and the browser load time itself. So we've kind of gone through the different layers. If we looked at data collected from New Relic browser and the JavaScript agent, the time spent processing the DOM or rendering the page also spiked. 9.9 seconds on average, but if we were actually looking at our synthetic traffic, so what we were actually running in different global locations, it was essentially off the charts. It was around 20 seconds from 1.4 seconds. And the lesson there, and what we learned looking into it was really that choice of instance. It was that this T2 instance, per Amazon's disclaimer, it was taking more of 5% CPU on average over 24 hours, and we lost that benefit of that high-frequency Intel CPU, to use Amazon's marketing verbiage. So yeah, for this particular application, the T2 instance, which was being hit with a fairly constant amount of traffic that exceeded that threshold, was a really terrible choice, and the load time went up a massive amount. So our first our first attempt to really increase page load time was more successful than I think I really wanted it to be. Moving up, so we're going to roll back each of these changes for each of these experiments. So we went back to the larger instance. This application that generates this page, all the images, the JavaScript, the CSS, it captures all the traffic, is written in Go, and we're just going to do some simple things to essentially slow down Go, despite its kind of performant reputation. One thing that was deliberate in designing this was, we just need to generate some sort of computational load. So every pixel of every image, and there are about 14 images on the site, is randomly generated. Just a for loop, we're generating a random pixel. And that itself, not surprisingly, is the most expensive transaction. So generating the images, because every single pixel is random per request. Not surprisingly, you can see the purple there. It takes up a massive percentage of wall clock time among all other transactions, 77%. And the other endpoints, which are delivering the JavaScript CSS, or just the root path, or the favicon.ico, relatively a much, much lower number. But if we look at the actual timing of that, it's still relatively fast, which I guess we can thank the Go runtime for making that operation to generate random pixels for all these images per each request for multiple sessions, a relatively quick thing. So the easy thing was, well, we'll define an environment variable. This is running in Docker, so we'll pass it using the -e flag. If slow image exists, we're just going to pause for 1 second. And as expected, that had a pretty big impact. The web transaction time, the apdex goes down enough where it starts to flag the transactions in red. And that's a pretty successful experiment, as more or less expected. But also wanted to tweak the Go runtime to kind of get deep into the Go internals to ultimately force the Go garbage collector to run more frequently. And we do track the Go runtime internals under the Go runtime flag if you're running a Go application and monitoring it. But using this Go GC environment variable, which is defined by the Go runtime, we essentially force it to garbage collect more frequently. So after deploying the app around 4:55 or so, we see the pause frequency spike, and the percentage of pauses as wall clock time also spike as well. So unlike the explicit code pause, we're ultimately getting the garbage collector to pause the application for us. The theory being, hopefully that the response time will also increase as well. And so then it's running, we have traffic being sent from 10 global locations in New Relic Synthetics. Synthetics is ultimately kind of a Chrome browser as a service around the world in different data centers. It hits the page we created and gathers performance metrics. So this is load time directly in New Relic Synthetics. But you can see right around 4:30 when we push the change and all these synthetics changes run again, the load time drastically spikes for every single global location, as expected, because this isn't just for users in one part of the world. And if we look at how that actually impacts the time, it goes up from 1.4 seconds to around 5.3 seconds. So kind of that idea of pausing the code, which could potentially be a stand-in for an external call or a slow external service call, that pause, is and very much was very significant in decreasing performance and increasing page load time there. So kind of our Go experiments were pretty successful. Kind of moving up the stack, the next process would be talking about the network. And the network is kind of my personal favorite in ways of kind of unoptimizations, because traditionally, if you work on a fairly small team and you don't have a network engineer around, the black box of like the stuff that happens between the mobile app or the browser and your backend servers, you really have no control over. So there's no one really around that says, oh, I really know how to fix slow performance for a particular network in Europe. But I think it's very much something we can solve from a design perspective or using new protocols. And so when we talk about network stuff, I think it's especially interesting, and especially interesting if you're building something for a global audience. And just to kind of a brief aside on network latency and why I think this network stuff is particularly important. AWS just launched a new data center in Ohio, and they published very impressive round-trip times considering its transcontinental data transfers. So the round-trip time between the Ohio data center and the one in the US West 1 or US West 2, which is Northern California and Oregon, 52 and 68 milliseconds. So not that bad considering it's crossing the entire continental United States. But we know based on how internet protocols work that over time, with very complex sizes, this problem of network latency becomes quite a big deal, especially for delivering apps and sites to a global audience. And kind of a slightly academic aside, it really gets down to the number of round trips when you establish a new TCP connection. So HTTP, the protocol that powers the web, until very, very recently, there are some experiments, but ultimately it's powered over TCP. And when you open a new TCP connection, it requires 2 round trips to actually get the first byte of data. And if you're making connections to different hosts, you obviously can't share a TCP connection. And if you're using TLS, so a secure connection, the first time that TLS key exchange is negotiated, that's additional round trips as well. So this idea of round trips and minimizing round trips is so important when talking about network latency, and it's been a primary focus of new protocol developments in HTTP2 and coming very soon quick as well. So there's actually this really interesting setting you can use in a header that forces the browser to disable TCP connection reuse. So typically, almost every site has this connection keep alive header sent, which basically says, if I'm going to be making multiple HTTP requests to your remote endpoints, reuse the TCP connection. Keep it open because we know there's that cost in reopening it. And there's also theoretically a cost on the server side as well in opening up new sockets. But we enable this setter, we set it in our Golang code, and the browser doesn't do it. We're also going to do things like just making sure we aren't trying to optimize the bandwidth at all. Go by default, if you're writing a simple HTTP server, does not gzip and does not minify, so we're good on there. We're also going to set a header that explicitly disables any caching by any intermediate proxies, CDNs, or the browser itself. So make sure that nothing at all can get cached. The first kind of sign that this was working, that the connection close flag was actually successful, was this small spike in number of received packets in the network view of New Relic infrastructure. And the reason behind that spike, which is pretty interesting, is those TCP handshakes. So as more handshakes had to be performed against this host, the number of packets increased slightly. Not a massive spike, but definitely noticeable in the graph there. If we go over to the application view, nothing much to see here. Because we're making it in the network, the application code's entirely indifferent and ultimately unaffected. But if we go into New Relic Insights, we can write a small query that actually looks up for all the connections we're making to the host, how many of those connections, what percentage took 0 milliseconds to open. And we know if a connection takes 0 milliseconds to open, there was no TCP negotiation or handshake. It's reusing that existing connection. So we go from around 83% on the sites down to around 20%. We're also using New Relic browser to capture some of the metrics, which obviously does use HTTP keep alive, so that's why it's not 0%. So some things are actually doing the right thing in terms of reusing the connection, but by disabling it, this absolutely drops pretty quickly. And if we look at kind of the scatter plot of New Relic synthetics, it gets actually pretty interesting. So if you look at like the purple down here at the very bottom, that's Portland, Oregon, and San Francisco. Not much of a change, not much of a delta between turning it on and turning it off. But the farther away you get from the Oregon data center, specifically Sydney, Singapore, Brazil, it changes drastically, because for each of those TCP connection handshakes, you're talking about multiple round trips, and those round trips are absolutely correlated with the geographic distance between the data center and the browser that's running it. So you immediately see a huge spread for the international browsers that are far away from the data center we're actually hosting the application, which is a pretty cool way to visualize all the performance work that's been done and continues to be done around minimizing TCP round trips. And if we look at kind of the median impact across all these locations, it goes up from 1.4 seconds to 2 seconds. So absolutely significant, but perhaps if you were in San Francisco or Portland, far less noticeable than someone in Brazil or Singapore after the switch is made. So it's a pretty interesting way to kind of see that play out for a simulated global audience. Between all of that, though, there's a much easier way that we don't have to deal with TCP to increase network latency, and that's just make sure the distance between the browser and the server is really, really far. And if we look at all of the AWS regions versus where we are in San Francisco, one of the farthest away is around 8,500 miles. That's Great Circle distance. And that's, of course, AWS in Mumbai, AP South 1, and that's measured against San Francisco Airport. So why not just move our server that's hosting this Go application to India? And if we do that, basically what you expect does happen. This is filterable geographies in New Relic browser. So each time there's a browser run that's hitting this site, it's collecting timing data and what the IP address was of that browser, so we know geographically in the world where it was. And not surprisingly, we see a bunch of red everywhere except Japan. Singapore would also be green, but it's so small, it doesn't really show up. As expected, immediate impact. Perhaps Japanese users do like that change. But we also see the load time after a small spike also drop by around 1.5 seconds in Singapore. So the idea that where the server running the application is absolutely supported by this. One kind of curious thing though is that we're running it across all these global locations. It would be reasonable to say, I opened a data center physically closer to where these synthetic instances are running. So I've shortened the kind of as the crow flies distance between the browser and the data center. I would expect where that's true, my page load time also decreases. Everything else held constant. But for certain locations, specifically Sydney, that's not at all true. The time actually increased. And that's simply a reflection of that, there is no direct fiber optic connection between Sydney and AWS Mumbai. It goes, on some route around the world, depending on, undersea cable routes and different peering agreements. But the idea that, minimizing geography is always guaranteed to increase load time, definitely not strictly true based on this experiment. And on average, the load time increased by about 1 second by moving it to the AWS India data center. And that's mostly a reflection of that we put a lot of monitors in North America and Europe and also South America and Brazil. So pretty interesting when talking about kind of geographic distance, network latency, and how that impacts how quickly the page loads. And lastly, one of my favorite things as someone who did some front-end work is just, there are so many different ways and so many kind of like tips and tricks that have built up over the years of things you should do when building a front-end application that make performance faster. And there are hundreds of these. Some are more important than others, but the conversation has always continued. Well, what's the kind of the set of best practices that make browser applications, so code that you write that runs in the browser as fast as possible? And so, a big one and one we've known for a time is that CSS blocks rendering, so let's deliberately delay it. Let's put it in the body. We'll add some crazy imports and just send a lot of CSS over the wire that's slow to parse, make it uncacheable, and ideally far away from the user that requests it. We'll follow somewhat of a similar methodology with JavaScript. Put a lot of libraries in the head tag, again, blocking. Load a lot of unnecessary JavaScript, and don't take advantage of any of the newer things like the async script attribute. And the difference between with it turned on and turned off, there's more. So we'll use a bunch of web fonts loaded from a remote server. And why use one JavaScript framework when you can use most of them? So between all that, between turning it on and turning it off, yes, in browser, the page load time does decrease when we turn this all off. It drops. That's pretty much as expected. But I wanted to also show the page loading with it all turned on. I'm not sure if we'll make it all the way, but you can see it loading. So here come the images. It's pretty painful, and I think if we remember those like powers of 10 metrics from earlier, if you're staring at this and you imagine you were actually trying to complete something, it's not that much of a stretch to say after 10 seconds you're definitely back on Twitter. Your mind has absolutely gone elsewhere. So that's this is the upper bar of the performance with all these optimizations turned on, which is interesting and useful. But if we look at all of it together, from all these optimizations, a fairly, not entirely random, but just a kind of a set of things we kind of guessed would impact performance, we definitely exceed the threshold of a reasonably fast page across all tiers. And we know that each of these decisions impacted how quickly the page loaded in a browser, as expected. So I don't know. I mean, the difference between this aggressively unoptimized site, I stopped at around 30 seconds. If I do turn on the things you'd expect, remove the terrible browser unoptimizations, use the right headers, have a reasonable caching policy, it does go down to 800 milliseconds. So the difference between something that's deliberately never optimized and something that just kind of lazily optimized is quite large, especially in terms of this customer experience meter we've described. So I don't know. It seems kind of like an academic exercise that we've done all these things and we say, oh wow, that impacted customer experience. But I think the point is, and what I definitely want to say is that choices like this, maybe not as extreme as moving all your your application code to a data center in a remote country, but different versions of this stuff happens all the time, and for really perfectly reasonable decisions. And to kind of tell the story of that, I've kind of created a story. I'm calling it Choose Your Own Tech Stack, based on an 80s series of books you may or might know. And the story here is just called Tears of the Browser. And so if we kind of go through the stack and what reasonable choices would lead people to kind of go down this path, I think one super common one is just kind of choosing the data center of least resistance. And I mean, it's a fairly common idea that you need to launch code to a data center. It's late, and there's quite a lot of diligence required right now to choose the right availability zones, or even to choose the right AWS region or public cloud region. And oftentimes, it's just much easier to use what's configured and launch it, even if maybe that data center doesn't necessarily serve customers using it or the geography of customers using it in the best way. Launching in AWS US East when 45% of the customers or people using it might be in South Asia, not a great choice, but also a hard choice, and one that definitely comes at a cost. Similarly, and this is absolutely a true story, that you occasionally get things from people far away saying your application's slow, but you notice that everyone complaining the application's slow is in a particular region or geography. In this case, say a particular cellular network in France, and you kind of have a choice there. It's either you have to get super deep into network performance metrics and understand how you could maybe optimize that, or maybe roll out a new protocol. Or you can choose to prioritize feature work instead, and that's not an unreasonable choice, and it's not a lazy choice either. And similarly, when we were talking about kind of new application architectures, or decisions we make when we're learning a new stack or a new tool set, it's very easy, and it's not at all unreasonable, I think, to choose a popular, well-supported framework to kind of enable that. And you can get kind of wonky and go like super deep on things like Go runtime performance metrics, or even looking at stuff how the Go garbage collector might vary between different versions, or there might be a huge reason to upgrade to the latest version of the Go runtime because the garbage collector performance for your application would be significantly better. Those are all like really hard questions, and it's not at all a bad idea or even a negligent idea to say, what, we're going to use this framework that's well supported, and we're going to go from there. And lastly, this one is kind of one of my favorites, just based on personal experience, and that's the never-ending quest to find the fast and modern JavaScript framework. There's this great desire in the front-end community, if you're in it or not, to use kind of modern tools and frameworks to enable faster development, to enable better applications, just to kind of improve your day-to-day as someone who's writing JavaScript code. And for lots of sites that have legacy applications or tens of thousands of lines of old jQuery code, the choice to say, what, we're going to migrate all of that at the same time to a new framework essentially becomes a rewrite. And so, depending on the page, depending on the application, it's not that uncommon to see, and we do see this in data collected in web page in the HTTP archive, that many people are loading multiple versions of JavaScript libraries, even though they essentially accomplish the same task. And so that's not necessarily shocking or surprising. But I don't know, I mean, between all that, I guess there's kind of getting at this idea that between all these decisions we make and all of the things we look at, we can use this data to ultimately understand how the changes impact the things we build and use that to build better things. And I don't know, for this application, this is the dashboard and insights that it was created. But we're pulling data from all different pieces of the stack, from the network. We talked about the 0 millisecond request connect time, to the infrastructure data, how the EC2 hosts are performing, to the app, kind of getting into granular Go routine data, and of course the browser as well, which is essentially everything else. But I think it's really this relationship between different components of the stack and understanding how it changes over time that's really the challenge for building kind of fast and performant web applications. And fortunately, I think there have been great talks this morning and great talks the next day and a half that'll, well, really day and a quarter, that'll absolutely get into this. So I think there's a really great opportunity to look at how these numbers fit together and ultimately use that to build better software. And on that note, that's about it for me. I'm around for questions later, and thanks very much for sitting through and making browsers cry.